A single agent on a single task is the simple case. Real research asks for more. Long, multi-step computations, one agent checking another's work, hours of unattended running, and honest reporting when something breaks. Orchestration is the practice of composing agents and operations into a workflow you can trust. This video assembles that workflow and shows that the loop it builds is one ingredient short of evolution. This assumes you are comfortable directing an agent through a tool calling loop and reading the diff it produces. The loop we build repeats 4 steps: propose, evaluate, select, repeat. Add one more, a mutation step, and it becomes an evolutionary algorithm. That is the pivot the series turns on. Here is the ground we cover: pipelines and parallel execution, the proposer, the critic, and the verifier, spawning subagents, external memory, reliability, retries, logging, and honest failure, and the loop that ties it together. Start with the shape of a workflow. A workflow is a directed graph of operations. Some steps depend on the outputs of others. Some can run in parallel. The orchestrator's job is to schedule them correctly and collect their results. The simplest workflow is a pipeline, a straight line where the output of each step is the input to the next. A 3-step research pipeline retrieves domain knowledge, hands it to a proposer that generates and scores candidates, and selects the best. Each step can be a model call, a tool invocation, or a subprocess. The pipeline is the wiring that connects them and carries one step's result into the next. Some operations do not depend on each other. Several proposers can generate candidates at the same time, or a critic can score one batch while the next is still being produced. Parallel execution runs these independent operations concurrently and cuts the wall clock time of a run. But parallelism brings one hazard: non-determinism. The order in which parallel operations finish is not predictable from one run to the next. If the final choice depends on that order, say to break a tie, the result can change between runs. The discipline is simple: set your seeds and record exactly which candidates were selected, so a run can be reproduced and explained later. The most common multi-agent pattern in this course pairs 2 roles. A proposer generates candidate artifacts, model expressions, hypotheses, experimental designs. Its goal is breadth, producing diverse, plausible candidates quickly. A critic examines each candidate before it reaches the evaluator. Its goal is precision, filtering out the ones that are obviously wrong. The critic enforces the constraints the scoring harness does not check: that an expression is dimensionally consistent, that it is valid Python, that it is numerically stable, and that it has not already been tried. Filtering before evaluation saves money, because evaluation may be an expensive step, a model call, or a heavy computation. This proposer-critic loop is the pattern engineering writing calls the evaluator optimizer. The evaluator scores the survivors, the selector keeps the best, and the best feed the next round of proposals. A critic checks soft constraints. A verifier goes further. A verifier is an agent whose explicit task is to disprove a claim or detect an error. Where the critic asks, "Is this plausible?" the verifier asks, "Is this actually true?" Suppose the primary agent claims, "The features are all non-negative, so log transforms are safe." A verifier does not take that on faith. It runs a check against the real data, computing the minimum feature value and testing whether any value is 0 or negative. If a single feature is 0, the claim is false, and the log transform would have failed silently. The verifier catches the mistake the proposer made without noticing, the kind of error that survives precisely when no one is asked to look for it. That is the verifier in one line. The proposer-critic wiring is static. The agents and their connections are fixed before the run. A more flexible pattern lets an orchestrator spawn specialist subagents on demand. It calls a tool that launches a fresh agent with its own context window, its own tools, and its own task, then collects the result. A research orchestrator might spawn one subagent per candidate dataset or one per section of a report. Each subagent works in an isolated context, so the orchestrator's own window is not flooded with intermediate detail, and independent questions are explored at once. The cost is real, roughly an order of magnitude more tokens than a single agent. So the topology pays off for breadth-first work, whose parts are genuinely independent, not for tightly coupled tasks. And when parallel agents must write, not just read, each needs its own working directory, so their changes cannot collide. A single session agent remembers its history inside the context window. An orchestrated run that spans many rounds or spawns parallel agents needs external memory, state stored outside any single agent's context. 4 things are worth remembering. The expressions already tried, so the proposer does not waste budget on duplicates. The best results so far, so the selector can always return the best discovered. The failure modes, the candidates that crashed the evaluator and the errors they threw, so the proposer can avoid them. And the run configuration, the seed, the model, the dataset version, so the run can be reproduced exactly. Written to a file, this memory becomes the primary artifact of the run. It is what lets an interrupted run resume and what lets a finished run be reported honestly. How much machinery does that memory need? At its simplest, a single JSON file, updated after each round. That file is the reproducible floor, the minimum that keeps a run resumable and honestly reportable. It is not the ceiling. Production agents back external memory with a vector store, so that already tried can match a semantically equivalent candidate, not only a string-identical one, and with episodic memory for runs that span many sessions. These richer stores are the same idea with a better index. Recent work formalizes what to keep across runs, distilling reusable reasoning strategies from past attempts and treating the agent's evolving context itself as the thing to optimize. An orchestrated pipeline that runs for hours must be built to fail gracefully. Start with the calls worth protecting. The operations that fail unpredictably are the ones that leave the process. An API call to a model provider over the network, or a query to a server behind the protocol we use for tools. Both cross a boundary the pipeline does not control. A retry reattempts a failed call after waiting. Exponential backoff makes each successive wait longer, easing the load on a server that is already struggling. The wait also carries a random jitter, because 4 workers that failed together would otherwise sleep for the same interval and retry in lockstep, recreating the burst. But retry only transient faults, the ones a second attempt could survive. A malformed request, an expired key, a missing tool, these fail identically every time. Wrapping them in a retry buys nothing and buries the real error. So the predicate is which exceptions the loop catches, not how long it sleeps. And when the budget is spent, it raises, rather than returning a fallback that only looks like a result. Reliability is not only retries, it is also seeing what happened and being honest when it breaks. A run without logs is a run you cannot understand afterward. Every orchestrated run should log its configuration, every model call with its token counts and latency, every tool call and result, every error and its resolution, and the final outcome. Then the harder discipline. A pipeline fails more often than a single script. When it does, surface the failure, do not hide it. A pipeline that silently returns a fallback is worse than one that raises. The silent one produces a wrong answer that looks right, while the loud one gives no answer but an informative error. So report failures explicitly. If nothing beat the baseline, say so. If 3 of 10 calls failed to rate limits, report the fraction. A failure report is not the sign of a bad system. A failure report that is missing is the sign of one you cannot trust. Step back, and the whole orchestration reduces to one loop, the generate, evaluate, select loop. Generate a set of candidate artifacts. Evaluate each one, scoring it on the reusable validation split, never the sealed test the final audit depends on. Select the top K by score. Then repeat, with the survivors informing the next round. Concretely, in one round, the proposer generates 5 candidate expressions. The harness scores them, 0.12, 0.08, 0.23, 0.07, and 0.15. With K equal to 2 and lower being better, the selector keeps 0.07 and 0.08 as the elites that seed the next round. Every run is this small story, repeated. This loop is an evolutionary algorithm in all but name. The one missing ingredient is a mutation operator, a way to derive new candidates from the survivors rather than proposing each from scratch. Add mutation, and generate, evaluate, select becomes the evolutionary loop. The pivot ahead is not a new topic. It is one ingredient added to a loop you already understand. Here is orchestration on one card. Compose chain operations into a pipeline and run the independent ones in parallel. Check a proposer for breadth, a critic, and a verifier for precision. Remember, external memory holds what must survive the rounds. Fail honestly. Retry only transient faults. Log everything and raise rather than hide. Loop, generate, evaluate, select, repeat. And the idea to carry away. Orchestration composes agents into a workflow that runs unattended and fails honestly. And the loop it assembles, generate, evaluate, select, is an evolutionary algorithm missing a single ingredient. Understand it and its failure modes, and the pivot into evolution is one step, not a leap.